Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software RFEM as well as our standalone program for wind analysis RWIND. The topic for today's presentation is CFD wind simulation with RWIND 2. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be joining me as your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. And if by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So as far as the content over the next hour today, I do want to give a brief introduction to our standalone program RWIND 2 and the topic of computational fluid dynamics, or CFD. We'll then move into our example where we'll begin in RFEM 6, where we can input in the wind analysis input and settings in order to run the wind analysis within RWIND. We'll take a look after we run the wind analysis, how those wind loads can be integrated back into RFEM for the structural analysis. We also want to consider the influence of surrounding objects as well as the terrain. And finally, we'll send a significant portion at the end of the presentation, reviewing the wind analysis and results and data output directly within RWIND. So a very common question that we get is the role of CFD and design standards. So we know that the engineering codes such as the ASCE 7, the NBC, the Eurocode all provide minimum engineering requirements and loads for safety considerations, and this includes wind loads. The ASCE 7 has 3 approved wind load methods. The first is the simplified method. So this should be used for very simple, symmetric, and short structures. The analytical method is for any structure that falls outside the simplified, but still considered a regular structure. And finally, we have the wind tunnel method. And this is for all structures that fall outside simplified and analytical and really are for irregular structures. So the question is that CFD is not listed here as an approved method. So how can it still be a useful tool? So on this next slide, I want to talk about the benefits of computational fluid dynamics and how it can be a cost-effective engineering tool for many useful applications. And notice that I have put emphasis here on the word tool rather than an approved method according to the standard. So CFD allows us to assess varying wind loads very early on in the design process. We can take our structure, apply the CFD numerical wind tunnel, and see the impact very on in the design process to see what type of structure modifications we might need to make. Now, standards only provide minimum wind loads. It could be the scenario that we actually need to apply higher loads than the minimum wind loads specified by the standards due to special cases. So for very complex structure shapes, for example. CFD should really be applied for structures that completely fall outside the standard with no minimum guidelines to follow. There are certainly many structures that are not addressed directly within the ASCE 7, for example. So we see how a program like RWIND could be useful. We also can take into consideration surrounding terrain or objects. So if we have a very complex terrain with many hills, maybe adjacent buildings, and we want to see how that impacts the wind flow on our structure, we can use CFD. Now, for very complex and irregular structures, of course, the ASCE 7 says that we must run a wind tunnel test. Well, we can use a program like RWIND as a preliminary analysis before we move on to the true wind tunnel test. And you can imagine that that's going to be a huge cost and time savings if we're able to run the preliminary analysis, maybe adjust our structure if it's very over-designed or under-designed before we move to a true wind tunnel test. We also can use CFD to determine occupant comfort with applied wind loads. So is this structure sufficient enough to not impact occupants that are inside? So all in all, complex CFD methods should be used for complex structures with no standard guidelines. By all means, we're not suggesting to use a program like RWIND for a very short, symmetric, rectangular building. It's clear that the code will have the minimum wind loads to be applied for these type of structures, but rather these complex structures that kind of fall outside of what the standard really talks about. So let us talk about the theory and background of this standalone program, RWIND2. It's actually a collaboration between 3 companies, including, of course, us, Delubal Software, but also PC Progress and CFD Support. It will apply numerical computational fluid dynamics to apply fluid mechanics simulation around objects within this numerical wind tunnel. We can see down here at the lower right a small picture of what this wind tunnel may look like with our structure that we'll be moving through today. It does utilize the Open Foam for Windows solver that was developed by CFD Support. It also utilizes the numerical solver RWIND simulation solver, which is related to the simple solver algorithm, and simple stands for the semi-implicit method for pressure-linked equations. So computational finite volume mesh that is required for a CFD analysis can be extremely time consuming. And the huge advantage of RWIND is that we have implemented this simplified model and will apply a so-called shrink wrap mesh around the structure for that finite volume mesh. And all of this is done automatically to correct most mesh problems that otherwise we would manually need to address. So if we take a look at the example over on the right, we have a flower. And at the center of the flower, we have zoomed in here on the right-hand side, there's quite a bit of detail going on. So you could imagine if we had to place this mesh over our structure to take into consideration all of this detail, it would be very time consuming. Not to mention we need to take care about open edges or overlapping triangles. So what RWIND will do is to automatically correct all of these issues for us. So we take a look at the shrink wrap mesh around this same flower. We've zoomed in here to the center. You can see that all of these details have been simplified and most of the errors have been corrected. Now, topics like the level of detail for our shrink wrap mesh, closing the opening size, mesh refinements are all adjustable, but these are inevitably going to affect the calculation time. Obviously, the higher level of detail, the more mesh elements, the higher the calculation time will take within RWIND. Now, this simplified model for this shrink wrap mesh is optional within the program. You can turn it off and to import in your own boundary lines for this mesh, but for 99% of us, we're probably going to use the default option where the mesh is automatically generated for us, unless you're an advanced CFD user. So with this new version, RWIND2, we have introduced the Pro versus Basic version. So in our first release of RWIND, we offered the steady flow simulation. This is essentially a flow field that does not change over time. So we're kind of taking a snapshot of that wind on the structure to determine the pressures and the pressure coefficients. And this is still available with the basic version. With the Pro version, we now have introduced the transient flow simulation with advanced LES turbulence model. So with the Pro, you'll have the option to run the transient flow or the steady flow. And we know that wind flow actually does change over time. And a few examples of this is the Kármán vortex street or vortex shedding. So now with this transient flow, we can consider these types of scenarios. We'll still use the initial condition using the steady flow, but we will define a total time duration and these time steps that we can actually view our saved results. And within RWIND, we can view the graphical and diagram time bearing results for each time step. And we'll see that in the second part of our webinar today. So we'll begin with our example today, and we will start off within our FEA program, RFEM 6. And you can see here I've taken the liberty to model our canopy type structure. And the structure might look a bit familiar if you joined us for our last webinar on aluminum ADM design. However, I did modify this one that it is entirely steel. So we can take a look at the materials over in our navigator on the left to see the materials like A992, A36, as well as our various cross sections that we have defined here. So when we want to consider integrating RWIND, we would right-click here to access the base data. And the base data would be the dialog box that pops up when we create a new model as well. And under the second tab here is all of our various add-ons that we can enable if we've purchased them. And you can see down here, the lower left, we have wind simulation. So we can activate that here. Now I've also activated the steel design add-on. So RFEM is responsible for the analysis portion. And then we can activate these add-ons here for the design. And today it would be design according to the AISC. Now we don't have enough time to go into detail on the actual steel design, but I do have a previously recorded webinar devoted to the entire workflow for steel design according to the AISC. Now, under the third tab, we need to define our standard here for our load cases and combinations, as well as our load wizards. You can see I have this set to the ASCE 7 2016, but we also have the NBC, the Eurocode, and many other international standards. And as I mentioned before, we have the AISC set for steel design, but of course the CSA standard and other international standards are available. So once we have activated the wind simulation within the base data, I'm going to go up here to my load cases. And I have already defined two very simple load cases, dead load and snow load. But we want to add a third load case here that we will give it the name wind load. And the action category is going to also be set to wind load here based on the ASCE 7. Now, typically, the analysis type is always set to static analysis when we haven't enabled any of those add-ons. But because we have enabled wind simulation, we now see a new analysis type here called wind simulation. Now we have a couple other tabs available once we enable this. And we'll begin with the second tab here. These are all of the analysis settings that will be used once we run the calculation within RWIND, but we can set these available now within the RFEM program directly. So if we edit the default option here, we can see several parameters, including the simulation type, which is set to steady flow. If we have the Pro version, then we would also have the transient flow available to us. We'll leave this as the steady flow for the first part of this example. Now we'd also want to set the density of the air. So factors like the altitude, temperature, atmospheric pressure, humidity, all of these are going to affect the density. So we'd want to input in these values depending on where our project is located. The kinematic viscosity would also be set, and this is the ratio of the viscosity to the density of the air. Now we have several other options we can turn on or off down here at the bottom. And the first is to consider turbulence. So we'll go ahead and leave that on. We want to take into account the effects of turbulent flow, which are characterized by chaotic changes of pressure and flow velocity. The second option here, the slip boundary condition on at the bottom boundary. So if perhaps we have a 20-story building that we've modeled, but we've really only modeled the top 10 stories, then we would want to turn on this option here, which will deactivate the bottom plane of the wind tunnel. So if we're only modeling a portion of our structure rather than the entire structure itself. Consider surface roughness. We can turn this on if we would like to. That will, of course, impact the wind analysis. We can also activate the user-defined dimensions of the wind tunnel. So we'll see in just a minute how the program automatically calculates the wind tunnel size based on our RFEM structure, but we can always override that if we'd like to. And the member load distribution, well, once we run the RWIND, we determine the wind pressures, we bring these wind pressures back into RFEM where they are converted to loads. We can decide here how we would like the member loads to be distributed. Concentrated is the default here. I would say this is maybe the most accurate, where we're going to get point loads at every FE mesh point. But we can certainly change this to uniform or trapezoidal for a more simplified application, where those loads will be averaged out along the length of the member. Now, as indicated within the PowerPoint, we will be utilizing the OpenFOAM solver. The finite volume mesh density. So this is the actual mesh inside the wind tunnel itself. And 20 is the default here. I'm going to decrease this to 10% just purely for our example today to run a slightly quicker calculation, but 20% or higher might be relevant for your project type. Under the steady flow, we can see here the number of iterations would be set. Maybe we need to increase this if we're not finding a convergence within the RWIND calculation. And the turbulence models available within this dropdown, K omega and K epsilon. If we want to know more about these turbulence models, we can always access our help manual, our online help manual down here in the lower left corner with this question mark, and that will take you directly to the DeLubault website. We'll go ahead and utilize the K omega for today's example. Now the residual monitoring, this is where we set the residual pressure, which is just essentially the stop limit for the calculation. You can see the default here is 0.001. So once we have input all of these analysis settings, we want to move on to the wind profile, which we can see over on the right is completely empty right now. So let us take a look at the default option here by editing the detail settings. So within the wind profile type, and we see here we have a drop down, we have two options. So the first is user defined. The wind profile is going to determine or to set the wind speed at the start of the wind tunnel as a function of height. And if we'd like to choose user defined, we see this table format. We see the height in the first column, the wind velocity we would define manually, as well as the turbulence intensity. Now, alternatively, we can choose here the ASCE7. Now, the ASCE7 is available because I've activated that standard within the base data. If I had set this to the NBC, would be able to generate the wind profile type according to the NBC as well. Within this standard setting, we have two definition types. The first is map and parameters, which we can access the GeoZone tool with this button here within the dialog box. This will launch a GeoZone tool available on the DeLubault website. Essentially what we have done here is we've taken several standards such as the ASCE7 and we've integrated them with Google Maps technology where you can just simply input your address of your project location and the basic wind velocity will be imported into RFEM. Now, alternatively, we can use this dropdown to choose user defined, and this will allow me to just simply type in the basic wind speed, let's say 70 miles per hour directly within these settings. Now, we also maybe want to adjust the exposure category. You can see here the turbulence intensity, as well as several coefficients that come directly from the ASCE7. All of this information is going to affect our wind profile over here on the right-hand side. Once we have set these settings, we click OK. We see our diagram generated over here on the right-hand side. The wind direction around the z-axis, this just orients a wind tunnel based on their structure orientation, and everything is according to the global x-axis. So at 0 degrees, we're going to see the wind move from left to right here around the structure. But of course, we can set this to a different angle. We'll see this a little bit later on as well. The terrain offset, if by chance we have modeled a basement, for example, within our RFEM model, we're really not wanting the wind to impact that particular location. We can always set this terrain offset based on the global z-axis to some value. And now you'll see here the wind tunnel. The program has automatically set the wind tunnel size based on our structure in the background here in RFEM. If we would want to override that, I had showed you previously where those settings are. So now that we have defined all of the wind simulation settings here within our load cases and combinations, I'm going to click OK. And under the calculate mesh settings, there is a second set of settings that we do need to address. Now, the mesh settings are typically set within RFEM to define the length of the FEA elements here. You can see the default is set to 1 foot, but now we have a new tab for wind simulation. So this all affects that shrink wrap mesh that I talked about within the PowerPoint. And the first option here is to determine the level of detail, with 0 being the lower factor, which is the less exact option, and 4 being the highest. So I'm going to decrease this to 1 for our example today, again, just for a quicker calculation, but 2 is the default. Remember, as we increase this number, the longer the calculation time. We also have the ability to close openings of our RFEM model with that shrink wrap mesh. So if we have window openings, door openings, we can actually close them for the wind analysis based on the settings here. This option to activate the visible objects only. So what you see in RFEM that's visible now will actually be taken into RWIND, and we'll get into this option a little bit later on as well. The option to keep the wind simulation results if the mesh is deleted. This is extremely helpful in the sense that we take our RFEM model, we run the CFD analysis in RWIND, we come back into RFEM, and we make just maybe minor changes that delete the FE mesh within RFEM itself. Well, with this option turned on, we'll go ahead and keep the wind analysis results, so you don't have to rerun those. Now, of course, if you're making major changes to your RFEM model, it's best if you go in and rerun the wind analysis, but this can be extremely helpful in order to save time without having to rerun that wind analysis each time. Okay, so we can click OK here once we have defined these options and go back into our load case here for wind load. And we have the ability to click calculate, and the program will run the calculation behind the scenes. We never even open up our wind. Now, alternatively, we can choose this button here, which the program will generate the mesh in RFEM, but it will launch the standalone program RWIND. And what we should see now is our structure being taken into this numerical wind tunnel where we can run the calculation. So here we are in RWIND, and sure enough, if I zoom in here, here is my structure brought in directly from RFEM. What I'm going to do under the simulation here is to begin my calculation, and I'll continue explaining a little bit more about what's going on. So we have set the mesh density of the mesh within the numerical wind tunnel itself. We can see that this mesh becomes a little bit more refined as we get closer to the structure. Here is our wind tunnel. The wind is going to be moving based on this red arrow here from left to right. If we're also interested, under the View tab, we can take a look at the model tree to deactivate the original model and activate the simplified model. And here is that shrink wrap mesh that we talked about within the PowerPoint, and we set those various settings within RFEM itself. So we can go ahead and activate the original model here, and we can go back to the wind simulation. So we can see here over on the right-hand side, we're running the calculation time based on that residual pressure that we've set at 0.001. So once the calculation is complete, the program asks us if we want to leave RWIND, we'll click no, and now we're presented with our results such as the pressure. The pressure is actively displayed here where I can move my mouse around to see those values. And any positive value here is pressure acting towards these elements, and towards the back we see a negative value, which would be a suction type pressure. Same concept for the pressure coefficient. We can move our mouse around to view those different values. We even can activate the pressure in and around the numerical wind tunnel. So you can see the pressure is activated with this slicer option, and I can kind of drag this back and forth in and around the structure. Same concept for the wind velocity. But we probably have a slight issue here. We know with this canopy type structure that we likely will have some type of panel on the roof, but we didn't model the panel because it's not so important for the actual structural analysis itself. The problem is that the program only knows what it knows. So we saw the members modeled in RFEM, it brings only those members here in RWIND. And you can see that the wind is currently passing through the roof structure. Now we could adjust the simplified mesh to close some of those openings depending on how complex it can be. But rather what we can do is take advantage of a new feature within RFEM. So I'm going to delete the results here. I'm going to exit out. And when we exit out of the program, we will be taken back into RFEM directly. So I cancel out of my dialog box, and I'm going to also cancel my visibility because I've actually already modeled these new surface features here at the roof level. And if I double click on this surface, the stiffness type is set to a new option here called load transfer. So notice that I don't have a thickness set, I don't have a material because we're not adding any stiffness to this structure. We're purely using these surfaces to transfer the loads to the members. Well, under the load transfer tab, we can set whether we would like this as one-way area load distribution based on the local X or Y axes, or two-way area load distribution based on both directions. So currently I have it set to one-way area load distribution based on the local Y. So I click OK here, and I can right click to turn on the local axis system of the surfaces, and we see those axes available here. So the loads will be distributed to these smaller purlin members and then inevitably distributed to the larger steel members after that. So once we have activated these surfaces, what I would like to do is to go back into the load case for wind, and we will launch our wind once again. So what we should see now within the model here is the surface is taken into consideration along with the members. And sure enough, that's what we see here. We can turn on the simplified model with the shrink wrap mesh, and now we see all of those openings have been closed. But in reality, if we'd really like to apply the wind loads to the roof panels only, and then to have them distributed to the members, again, the program only knows what it knows. So all members were modeled, these surfaces were modeled, everything's brought in based on the center lines, and the wind analysis will be applied to all objects. So what I'm going to do once again is to exit out of RWIND. And once we are back in RFEM itself, so we'll go back to the program here, cancel out of this dialog box. I'm going to hold down my control key to select only the column elements, the main beam between these two columns, and my two surfaces. And I'm going to create a visibility by the selected object. So now everything else is hidden in the background. Now these are just line elements on the surface. The only members that are shown here are the columns and the beam. And if you remember, under Calculate, Mesh Settings, we saw here under the wind simulation where we've activated the visible objects only. So if we go back to the wind load case and yet again launch our wind, we should see a slightly different model that's brought in here this time. So we'll go ahead and access our wind here, and sure enough, notice that all of my members are now not shown. I'll go ahead and start this calculation while we talk a little bit more. Again, we can activate this option to hide all of the objects within RFEM. So you see here only the surfaces are drawn. So what we should see with the wind analysis then is these applied wind pressures only at the surfaces. When we bring the pressures back into RFEM, we convert them to loads. Those loads will only be applied to the surfaces as well as the three members you saw here. And then based on that load transfer, the program will go ahead and distribute to the members. We can also take a look at that simplified shrink wrap mesh so you can see quite a bit more simple without all those members included. Okay, so over on the right-hand side, we can see our diagram of the residual pressure. We've reached that 0.001. We don't want to close our wind. We'll take a look at the results here. Now we're seeing a pressure at the top side of the surfaces. We can kind of rotate these around. We'll have a different pressure on the underside and of course along our members. We also can activate here the velocity vectors. The velocity vectors might be interesting because they show the magnitude and the direction of the wind flow throughout the wind tunnel. Again, with the slicer option, we can kind of drag that to see how those velocity vectors change. And of course, we can activate here our streamlines. And our streamlines, we can also show the flow animation, just how those particles move through the wind tunnel and how the structure affects the wind flow. Okay, so now that we have solved for our results here within RWIND, I will close the program and we'll once again be brought into RFEM. Now, when I cancel out of this dialog box, what we can do is to cancel out this visibility mode, and we can actually display our wind tunnel directly here within RFEM. So we can see our wind profile over on the left-hand side here. And now that I brought the wind pressures, we've converted them to loads within RFEM itself, we actually have to run the calculation here for the true static analysis. So we'll go ahead and start this calculation. Once that's complete, we can deactivate the view of the loads here and zoom in. We now have an available tab to us in the project navigator for our results. So this is purely the static analysis for those wind loads. So we're taking a look at the global deformations right now. We can modify the deformation view to be colored cross sections. And we can see, of course, as we'd expect, the wind flow from left to right here, the deformations shown from the relevant applied loads. We're probably also interested in the member internal forces. So we can activate the member internal forces, such as the axial forces for the columns we can see, as well as all other members. We can turn on the bending moments. If we'd like to filter this further, under our Views tab, we can filter by member, members by the cross sections that have been defined. So I can activate only my channel sections, for example. And if I right click to show the hidden objects in the background, these particular members were defined with member hinges, so they should more or less act as continuous members, and we can see that defined here by the moment diagram. So we'll cancel out of this visibility, and of course we have our support reaction shown to us. Now we would like to compile the wind load along with our other load cases, dead load and snow load, and the program has automatically generated those load combinations for me according to the ASCE 7. So I see here the factored load combinations according to LRFD here shown in orange. We have our unfactored load combinations or ASC, which we can see here in red. If we take a look at one of these and display our applied loads, we have snow load, dead load, wind load all applied to the structure. And once we have completed the load combinations, we also are interested not only in the static analysis, but the steel design. So if you remember at the beginning of the presentation, I activated the steel design add-on. This will go ahead and run the strength limit state and serviceability limit state according to the AISC. So I can run this calculation just quickly. The program will cycle through my factored load combinations, my unfactored load combinations, apply the AISC design equations, and now we're presented with our results here, both in table format as well as graphical format. So I can view the design results by member and take a look at my table and all the controlling checks here. Now for any one of these checks as well, I can access the design check details, which are going to show me all of my code equations in detail. My variables and the code references are shown here on the right-hand side. So this is new within RFEM 6, very transparent in understanding exactly where your numbers come from. Again, not enough time to get through the full steel design workflow, but you will want to refer to that previous webinar for more information. So if we go back to this wind load, and I'll go ahead and turn on the display of the loads, we only have wind acting in one direction, and we know in reality, of course, that's not the case. Wind can act in any which way. So unless we have a very completely symmetric structure, we probably want to take into consideration more directions. So how do we do that? Well, going back to my load cases here, I can rename this original load case that I've defined Wind1. And I can come down here to the lower left corner and make a copy. So when I make a copy, I can rename this to WinLoad2. Now, all of my wind simulation settings are already defined. I made a copy of that. We don't need to redefine anything here. The one change that I do want to make is the wind direction about the z-axis. So perhaps I change this to 30 degrees. So I click OK. Program asked me to clear the results. That's fine. And I kind of zoom out here. Now we can see that the wind tunnel is set at a 30-degree angle from my structure now. So we would want to rerun this within RWIND. But the question might be, well, what if we have multiple angles that we need to take into consideration? Sure, we can manually create these load cases, but we have a nice tool within RFEM itself. So we'll go back to the navigator under the data tab, and to make this a bit easier for you all to see, I can right click here to collapse all of these trees. So maybe it's not so overwhelming. And under the particular tree for load wizards, I can expand this and we have the option for wind simulations. So I can double click this and what you will see here is all of my analysis settings I've already defined. My wind profile is already set to the ASCE 7, nothing new here. But this tool allows us to set the step angle. So for example, 15 degrees. And I want to start at 0 degrees and I want to end at 90 degrees. So all of my load cases now should automatically be generated. And if I visit this second tab here, sure enough, I see all of these brand new load cases, 0 degrees, 15 degrees, 30 degrees, all the way up to 90 degrees. So when I click OK, you'll notice now within my drop-down box, we see our two manual definitions of wind load, but then we see all of the automatically generated wind loads here. And the program will go ahead and combine those into the factored and unfactored load combinations as well. So we see wind 1, wind 2, 3, 4, and so on. It also might be an advantage here if we take a look at our view in the plan view, and we'll take a look at 0 degrees, and I'll kind of zoom in here and decrease this table. So here is the wind tunnel acting on the structure at 0 degrees, and as we cycle through these, we see that the wind tunnel adjusts its size as well as the orientation based on those step angles. So we'd want to rerun all of these various load cases within our wind, bring those loads back into RFEM, and then we can continue on with the static analysis and design. Okay, so now that we have defined here our various loads on the structure, we've seen a simple application of running the analysis in RWIND, bringing those loads back in here. We also might have the question about the influence on the wind simulation for surrounding objects. So perhaps this structure is being used as some type of bus shelter. And we know underneath the bus shelter, quite common, we might have wall elements. And these wall elements further protect people from the elements such as wind loads, rain, snow, whatever it may be. So what I have done here under a separate model, which I can go ahead and open this up in RFEM, is to model 3 surface elements. Very simple. I purely have modeled them for the geometry only. Notice I'm not supporting them. I'm not running a structural analysis on this. What I want to do is to go to File, Export, and I'm going to export this model as an IFC file extension. So when I export this to IFC, I'll save it to my desktop or whatever folder on my computer that I would like. And now we go back to our original model here. And we have the ability under File to import in an IFC file. So I import that IFC file that I just created and saved. The program asked me where I would like to import it. I'll import it right directly to the origin. I click OK. I click OK, we'll turn this to a rendered view. And now we get an additional tab here in our navigator for the IFC import itself. And sure enough, here are these 3 walls. Now, these are IFC objects. They are not surfaces within RFEM. I can always right-click to convert it into a surface where I would need to define the thickness, the material, I would need to support these walls, but this would be running the structural analysis on these wall elements itself, which I'm really, again, not concerned with. I really just want them for the wind analysis itself. So we'll see in just a minute how we can import those into RWIND. But along the same topic, what about terrain? So currently everything is shown on a completely flat terrain at the base of the structure. Well, if we go back to our base or to our navigator data here and we right click to visit the base data dialog box, we've added a new feature in RFEM 6 for terrain considerations. And under this drop down, we can consider a horizontal plane, which, okay, maybe not so interesting, but we can consider an inclined plane. And I can create a new coordinate system here by choosing my option to create a new coordinate system that's defined by a point and 3 angles, where I can rotate this -5 degrees about the global y-axis. I click OK. Maybe I want to change my terrain dimensions to 35 feet by 35 feet. I click OK. And now what we should see here is this terrain displayed at the base of our structure. And that's all based on that 5-degree incline that we have set within that user-defined coordinate system. And this can be brought into RWIND as well. But the question is, what if we have a much more complex terrain? Could be argued that slope terrain, maybe a single hill, can easily be accounted for with the various factors from the ASCE 7 to adjust our wind profile, for example. Well, if we go back to this base data dialog box and under the terrain, instead of choosing an incline plane, we also have this table option. When I choose the table option, I get an additional tab here where I can input in the coordinates of my terrain based on the X, Y, and Z locations. I could even create an additional RFEM model with all of the nodes defined in my terrain, copy and paste the nodal points, or in our case today, you can see here I have generated an Excel file based on the X, Y, and Z coordinate points. So I can take all of these and I can copy them. And I go back to my RFEM model here, and I could import in from Excel down here at the lower right, or I could just simply hit Control V to paste in all of these various points. So now what we should see when we click OK is a much more complex terrain here. So we see this structure kind of sitting on top of this hill. Now, before we go back into RWIND, remember we don't want to bring over all elements. So what I'll do here is to highlight the IFC elements and my column. I'm going to hold down my control key to select the beam, my 2 surfaces here, and I'll create a user-defined visibility where the rest of those elements are hidden in the background. The terrain is already active. And under the Calculate Mesh settings, it's important that we go back to this Wind Simulation tab to initially turn on the terrain considerations, which may be turned on by default. We can see the terrain from the model will be brought into our wind, but we also want to turn on the surrounding model, including the IFC objects, and we can check this all option. And now the IFC objects that we imported for our walls sitting underneath the structure will also be taken into our wind. So I can click OK here, and what we should see if we take a look at our load case, we can jump back here to the original wind load case under wind simulation as we once again want to go ahead and launch our wind itself. But by all means, again, you can run this calculation silently in the background. You don't necessarily have to open up our wind every time. But let us just take a look at what has exactly been changed here. So if we zoom in here and maybe we go to the model view, we can see our terrain was brought in. Perhaps we'd want to make our terrain larger to fill up the entire wind tunnel, but you can see ours is defined here as well as those IFC objects. So now we should see pretty different results when it comes to the wind pressure in and around the structure. Now, we've already have a general sense of how to run this calculation, what our results look like. So what I'd like to do now is to take this model here and we'll move on to a transient flow. So under simulation parameters, keep in mind that RWIND is a standalone program. You don't necessarily need to bring in your RFEM model. You can import STL files, for example, and run the full wind analysis, again, as a standalone program. So these simulation parameters that we're seeing here are exactly what we set in RFEM. But if we're using RWIND as a standalone, we could set these parameters here, or we can even make changes after we bring the model into RWIND. So for our case today, remember we've been running a steady flow, but we can change this to transient flow now if we have the pro version of RWIND too. We now have an additional tab available to us where we can actually set the simulation time and time steps. When we have this option turned on, the program will automatically suggest a total time duration here of 16 seconds. And the program will also save the results at every 1.6 seconds. Now, once we finish the calculation, the master time layer here for RFEM, this will allow us to choose which particular time step we'd like to export back out to RFEM. Clearly, we can't export every single time step, so we'd want to choose which time step to export for that static analysis and design. So what I will do here is to open up an already saved model. The transient flow will obviously take just a couple more minutes to solve for. So here we can see our results that will be available to us. If we revisit the simulation parameters under the transient flow, we run the calculation, you can see here all of the various time steps that we can choose to export to RFEM. Okay, so what we want to view is the pressure on the structure, and we zoom in here. So not only do we have a pressure on the surfaces, on our members, but now we're also seeing a pressure on our IFC objects here. Well, because we're now running a transient flow, notice that we have a new section down here. And within this section are all of our saved time steps. So we can activate, for example, the first time step of 1.6 seconds. And I can actually scroll through these, and you should see the pressure changing here graphically on the structure as I kind of move through these different time steps. We can even activate the flow animation here automatically. You can see the program is moving through each one of those time steps as well. Same concept for our pressure coefficient. As we kind of cycle through these, we see the pressure coefficient modified over time in the same format. If we take a look at the velocity, so this might be interesting here if we activate the wind velocity in and around the structure. And I'll turn this to an elevation view here, and we'll kind of zoom out. We can activate this flow animation. We see how the velocity changes over time, not only around the structure, but we also see the velocities. We kind of move down this terrain hill that we've set and brought in for the wind analysis considerations. Same thing for the velocity vectors. So if we activate this flow animation, zoom in here, we can see those arrows changing as well as the colors indicated by the velocity magnitude. Okay, so same concept here that we saw for the steady flow, but of course now we have this whole time layer section available to us with the transient flow. I now want to go through several new features that we have added to RWIND, and this is available in both the basic and the pro version. And we'll kind of move through these from top to bottom here. So under our project navigator, the data option, you can kind of feel that this has the same look, same workflow as RFEM itself. So we're over here in this navigator, and we have this options for zones. And if I jump to the zones tab, what I have went ahead and done before the calculation is run to create 3 zones. The first zone is roof 1. So this is going to be the left side of the roof. I created a second zone for the right side of the roof, zone number 2 here. So we can see we just added these elements to that zone. And finally, we have zone 3, which is going to be the columns themselves. Now, if I select any one of these other options or objects within the model, you can see they're all assigned to zone 0. They do not have a zone assigned necessarily. So how can this help us? Well, if we go back to the simulation and we're taking a look at the pressures on the structure, and any one of the time steps is fine, under the sections tab, we can actually activate those different zones. So currently I'm looking at zone number 1 for the pressure. So you can see that this graphical view has isolated this single panel on the left. But we can also turn on the drag forces. So the total drag force is going to be shown only for the left side of this structure. I can activate zone number 2 and we see the new drag force indicated here on the right. Same concept for the columns. But we also can activate here 2 zones at once by holding down my shift key, and notice the drag force will update automatically here as well. So this might be beneficial for a very complex model where we're trying to isolate different parts of the structure to view the results. We can create these so-called zones. So going back to the data tab, in addition to the zones, and let me actually turn back on the entire model, we have here materials. So I can right click to create a new material, and I've defined this material here, which I've titled roof, where we can turn on the surface roughness. So when I turn this on, I can define the sand grain roughness height. I can also define the roughness constant. Once we've created however many materials we'd like, we can assign the material back under the zones. So notice if I double click zone number 1 here, I've assigned the material roof. Zone number 2 for the right side of the roof, I've also assigned that same material, but my columns, if I double click on this zone, have no material assigned. So we can create multiple materials, assign them to multiple zones to apply different roughness constants in order to affect the wind simulation. So that's also possible here within this project navigator. Another point is the point probes. So we can right click here to create a new probe. And when I do this, we can manually set here the number of points to 1. And now I can type in here the X, Y, and Z coordinates of where I'd like to apply this point probe. Now, alternatively, and probably the easier option is just to set this graphically. So when I choose this option, I can click on particular points of the structure, whether it's the left side, the right side, maybe a member, or even down here at those IFC objects. And those point probes are going to show me the pressure coefficient, whatever results I'm looking at currently on the structure. So when I click apply and finish here, you can see that as we scroll through these different time steps, the program is automatically going to update these point probes as well. Now, I have applied those point probes just essentially kind of anywhere where I clicked. We also have the option to right click to create a new probe, and I'll choose this option to set graphically. And instead of applying to the mesh surface, we can apply based on a cut plane. And I can apply this based on, let's say, 4 feet here in the Y plane. And now when I go to apply those point probes, I'm kind of confined here to this particular plane option in the global Y direction. So when I click finish, what we should see here are those point probes oriented along that line. Of course, we can cycle through the different time steps to see how these pressures are changing over time. But what else is helpful is we can actually view a graph here of the transient flow results. So when I turn this on, what we should see within our drop-down option here is point probes. So here's all the point probes that I have generated. And you can see how the pressure, or I can change this to the pressure coefficient, is changing over the course of the 16 seconds. I even can hold down my control key to add multiple point probes. So we see negative pressure down here with some of the point probes, positive pressure up here at the top. We can export this data as a text file. So pretty powerful if we're wanting to, again, view how the pressure coefficients are changing over time. Now, in a similar manner, we can view drag forces as well as a function of time. So we see the time duration 16 seconds. I can view the drag force for zone number 1 or zone number 2, which again is the left and right side of those roof structure, or I can hold down my shift key or control key to display the drag forces at once. So again, it's nice to view these visually, but it maybe gives us a better sense of what exactly the wind simulation is, how that wind simulation is impacting the pressure and pressure coefficient as a function of time here with these graph options. Okay, so we also similarly have what's called line probes. I can right click to create a new line probe, and I could define my line probe with 3 particular points. I would need to manually put in the X, Y, and Z. But unfortunately, we can't set these graphically here. So when I click on this, the program gives me an error. It says, nope, that's not allowed. It suggests use the graph along line tool instead. So what we can do is to select this option over here to graph along line probe. And I can change my orientation here of my plane to the global Y direction, and we'll just leave this at the point 0, 0, 0. So now I can click once at the left-hand side of this plane, and notice I'm just kind of following along this particular plane here, and I double click at my second point, and my line probe is automatically created right down the center of that structure, essentially a section cut. The diagram automatically pops up where we can see the surface pressure as a function of length here. But if we're interested in viewing the pressure as a function of length, well, this is just for this particular time step. So you see as I cycle through these how the graph is changing ever so slightly. Well, what we can actually do is to turn on all time layers if we'd like, and we can activate our legend here, and that's going to show us of all of our time steps how that pressure is changing along this particular line probe. Now we want to make sure to save this line probe, and we can see all of the options, the nodal points generated automatically. I click OK. And when we click close, we still have that line probe available to us. Now we can always double click on it to access that diagram again here. Keep in mind too, for any of these nodal, for these point probes or these line probes, we also can double click on them. And I had already mentioned that X, Y, and Z coordinates are shown here, but we can also activate the Show Results tab. And if I expand this out, we can actually see the positive pressure. So this might be the top side of this structure, a negative pressure for the underside, same thing for the pressure coefficients here. So if we're also interested in viewing our results in table format, this is possible. Okay, so the final results option that I want to show you that's new within RFEM is called point clouds. And we can activate here our streamlines of our structure, and the typical default option would look something like this. So the streamlines are kind of just based on this rectangle in and around the structure. Of course, we can activate the streamline settings here to change this to a segment, for example. We click apply, and now we have a single kind of line element here. We can use the graphical options to rotate this, hit apply, see how those streamlines are changing graphically. But another option is to set what we call line probes. So what I would like to do now is to go back to the option over here in the navigator, where we can right click to create a new point cloud graphically. And this should look familiar, this rectangular option here, because this was available to us in our streamline. So I can use my graphical options here to kind of decrease the size of this rectangle. Maybe I increase the height, and I click OK. So I've created my first point cloud, but I'm going to right click to create a second point cloud graphically. And I'm going to go ahead and grab the existing rectangle, move this over to the right-hand side, and I click OK. So now this second point cloud was created. Well, what this allows me to do under the streamline settings now is to activate under this drop down, instead of the rectangle or the segment, we can choose the option point clouds. And we want to display point clouds 1 through 2, so I can just manually type those in. I click OK, and now what we see are the streamlines only on the left and right-hand side of the structure. So you now have the ability to create these point clouds, different areas of the structure, so we can view more than one set of streamlines at a time. And we can activate here our flow animation, again, to see how those particles are moving in and around the structure through this numerical wind tunnel. All right, the final thing that I just want to mention before closing out this webinar is export options. This is also a common question. How can we export the results? Now, obviously we can bring these loads back into RFEM. We've already touched on this for the static analysis. If you're using RWIND alone, under results, we have the option here to export the values of point and line probes. You can see those can be exported as text files or VTP files. So that's certainly one option. The other option is we can export the results to ParaView. And ParaView is an open source data analysis and visualization program. It's free. You can find it with a quick online search. So if you're interested in viewing these wind results in just a slightly different manner according to ParaView, you can certainly export the results here as well. All right, so we will go back to our PowerPoint here. So as always, this is quite a bit of information. You can visit our website at deluval.com to learn more about RFEM, but also RWIND. This webinar will be recorded, usually available up on our website within a day. You can download the model that I created. You can open it up. In the free 90-day trial version of RFEM, we also offer a 30-day trial version of RWIND as well. Both of those will be full capability for that duration. If you have any questions about today's presentation or any of our products, feel free to contact us in our Philadelphia office with our contact info shown down here. Our phone number is 267-702-2815, and our email is info-us@deluval.com. So we will have more upcoming webinars as we continue to introduce the new features of our new generation RFEM 6. You can register at deluval.com under support and learning webinars. As most of you know, I will send out a reminder email about a week before these take place, so you can always feel free to register directly through the email as well. PDH certificates will automatically be emailed to all participants who were here for the full 60-minute duration. So this is a requirement of the states that we are pre-approved providers, that you are here for the full webinar duration to receive that PDH. If you watched with a colleague or you watched in a conference type setting and you were here for the full duration, go ahead and request that PDH. If you yourself did not register with your own name and your own email, go ahead and send us an email at info-us@deluval.com shown here. Just let us know who you watched it with, and we can go ahead and generate that PDH for you. Now, the PDH will not automatically be sent as soon as this webinar ends. It does take about a day or so in order to generate those PDHs. So just keep an eye out within the next day through your email. You should be receiving that. And with that said, I want to thank everyone for attending. And as always, we hope to see you at our next presentation. Thank you.